What if everything we see in the night sky, every star, every galaxy, even the vast emptiness between them, is just a tiny fragment of something far grander? Picture this: the universe isn't just a random scattering of celestial objects. It's woven together by an invisible, colossal structure, a cosmic skeleton holding everything in place. This is the cosmic web, the hidden architecture of existence itself, and it's one of the most profound mysteries in all of science. For centuries, we've gazed up at the heavens, mapping stars and charting galaxies, never realizing they were mere dots along the threads of something unimaginably vast. The cosmic web is like the universe's nervous system, a network of filaments made of dark matter and gas, stretching across billions of light years. These threads connect galaxies like beads on a string, guiding the formation of everything we know. But here's the thing, we can't even see most of it. This invisible framework shapes the cosmos, dictating where galaxies form, how they move, and even their ultimate fate. And yet, its secrets have remained locked away until now. In this journey, we're going to unravel 30 mind-blowing secrets of the cosmic web, each one more astonishing than the last. We'll explore how this hidden structure defies the laws of physics as we know them, how it might hold clues to the origins of dark matter, and even how it could reveal the ultimate fate of the universe itself. This isn't just about distant galaxies or abstract science. It's about understanding the very fabric of reality, the blueprint of existence. So, if you've ever wondered what truly lies beyond the stars, buckle up. Because what you're about to discover will change the way you see the cosmos forever. Imagine trying to map a city at night, but instead of streets and buildings, you're staring into an abyss where the roads are invisible, and the only clues are flickering lights scattered in the darkness. That's the challenge scientists face when studying the cosmic web. Its threads aren't just hard to see, they're made of something we can't see at all: dark matter. This mysterious substance doesn't emit light or energy, yet it makes up roughly 85% of all matter in the universe. It's the hidden scaffolding, the cosmic glue holding galaxies together in a vast, intricate network. Think of it like a spiderweb, but on a scale so enormous it defies comprehension. These filaments stretch across billions of light years, with galaxies clinging to them like dewdrops on a morning web. But here's where it gets even stranger. Without dark matter's gravitational pull, galaxies would fly apart, stars would scatter into the void, the universe as we know it wouldn't exist. So how do we study something that's fundamentally invisible? The answer lies in the bending of light itself, a phenomenon called gravitational lensing. When light from distant galaxies passes near these massive dark matter filaments, it warps like a car's headlights distorted by heat rising off a desert road. By studying these subtle distortions, scientists can trace the cosmic web's shadowy outline, mapping its structure one bend at a time. Supercomputer simulations take this even further, painting a dynamic portrait of how these filaments evolved over billions of years. They reveal how dark matter's gravity pulls gas and dust into its threads, sparking the birth of galaxies at their intersections. It's as if the universe is following a grand blueprint, one written in the language of gravity and shadow. And every new discovery peels back another layer, showing us just how much of the cosmos remains hidden in plain sight. Somewhere in the depths of space, an invisible force is tugging at our galaxy with the weight of 1,000,000 suns. The Milky Way isn't drifting aimlessly, it's racing towards something colossal, something we can't even see. Scientists call it the Great Attractor, a gravitational anomaly so powerful it's pulling not just us, but thousands of other galaxies through the cosmos at nearly 2 million kilometers per hour. Yet for decades, its true nature remained hidden, shrouded behind a celestial curtain known as the Zone of Avoidance. Picture staring into the night sky and finding a vast, empty patch where almost no galaxies are visible. That's the Zone of Avoidance, a region obscured by the dense dust and stars of our own Milky Way's galactic plane. It's like trying to peer through a thick fog with the Great Attractor lurking just behind it. Early astronomers detected its pull by noticing something bizarre. Every galaxy in our local supercluster was streaming toward the same invisible point, like iron filings drawn to a magnet. But what could exert such a tremendous gravitational force? The answer might rewrite our understanding of the cosmic web itself. Here's the twist: the Great Attractor isn't the final destination. Our galactic journey doesn't end there. Beyond it lies something even more massive, the Shapley supercluster, a megastructure containing tens of thousands of galaxies. This cosmic titan might be the real puppeteer, its gravity reaching across hundreds of millions of light years to orchestrate the motion of everything around it. But the Great Attractor's mystery doesn't stop there. Some researchers suspect it's not just a cluster of galaxies, but a knot in the cosmic web where multiple dark matter filaments intersect, funneling galaxies together like rivers merging into a whirlpool. So why hasn't modern astronomy solved this puzzle? The Zone of Avoidance isn't just a visual barrier, it's a data desert. Traditional telescopes struggle to penetrate the galactic dust, leaving huge gaps in our maps. But new tools are changing the game. Infrared and radio telescopes can see through the cosmic fog, revealing galaxies hidden behind the Milky Way's glare. Each discovery peels back another layer, showing how the Great Attractor fits into the cosmic web's grand design. It's a reminder that even in an age of space telescopes and supercomputers, the universe still holds secrets just out of view, waiting to rewrite the story of everything we think we know. The threads of the cosmic web aren't just cold, empty highways, they're supercharged rivers of gas so hot they could vaporize entire planets in seconds. These filaments, stretching between galaxies like bridges of fire, reach temperatures of millions of degrees, dwarfing even the core of our sun. But here's the catch: this inferno is invisible to the naked eye. It doesn't glow like starlight or burn like a flame. Instead, it pulses with X-rays, a searing signature detectable only by the most advanced telescopes in space. Enter the Chandra X-ray Observatory, a cosmic detective trained to see what human eyes cannot. Imagine tuning a radio to a frequency only dogs can hear. That's what Chandra does for the high-energy scream of these intergalactic furnaces. Every filament it observes crackles with the energy of countless supernovae, the remnants of violent stellar explosions funneled into these vast, flowing channels. This isn't just heat. It's a fossil record of the universe's most violent events, preserved in a labyrinth of scorching gas. So why doesn't this heat tear the cosmic web apart? The answer lies in gravity's relentless grip. The gas is so thin, just 1 atom per cubic meter, that even at these extreme temperatures, the crushing weight of dark matter holds it in place. Picture a hurricane trapped inside a spider's silk, unimaginably powerful yet eerily contained. And within these filaments, something extraordinary happens. The superheated gas doesn't just sit idle, it moves. Great cosmic currents carry material from one galaxy cluster to another, fueling star formation and shaping galactic destinies like an unseen hand. The discovery of these fiery filaments rewrote the rules of astrophysics. Before Chandra, scientists assumed the spaces between galaxies were near-perfect voids. Now we know they're alight with energy, a hidden circulatory system pumping lifeblood through the cosmos. Some filaments even glow brighter than entire galaxies, their heat generated by shockwaves from colliding galactic clusters, a reminder that even in the vast quiet of space, violence shapes the universe. But the real surprise: this heat isn't random. It follows precise patterns, tracing the cosmic web's architecture with eerie accuracy. By mapping these X-ray highways, astronomers don't just see where the universe has been, they're predicting where it's going. Every scorching thread is a clue, revealing how galaxies will drift, merge, and transform over billions of years. And as Chandra peers deeper, it uncovers even more mysteries. Pockets of gas hotter than theory allows, strange magnetic fields twisting through the voids, and whispers of energy with no known source. The cosmic web's highways aren't just hot, they're alive with secrets, and each discovery pulls us closer to understanding the furnace at the heart of creation itself. Between the blazing filaments of the cosmic web lie regions so empty, so hauntingly vacant, they defy everything we know about how the universe should behave. These are cosmic voids, the universe's ultimate ghost towns, some stretching over 300 million light-years with barely a single galaxy in sight. If the filaments are the crowded highways of the cosmos, voids are the deserts, vast, silent, and almost completely uninhabited. What makes these voids so unsettling isn't just their emptiness, it's how they break the rules. According to our best models of cosmic evolution, matter should be distributed somewhat evenly across the universe. Yet voids laugh at that idea. Picture dropping ink into water and watching it spread uniformly, only to find giant, ink-free gaps where the laws of diffusion seem to have been ignored. That's the puzzle astronomers face. These voids aren't just minor gaps, they're staggering absences, some so large they could swallow thousands of Milky Ways without a trace. Here's where it gets even stranger. Voids aren't static, they're growing. As the universe expands, these empty regions stretch faster than the areas dense with galaxies, acting like cosmic vacuum bubbles pushing everything else aside. This creates a bizarre phenomenon called void drift, where galaxies at the edges of voids are subtly pulled outward, as if space itself is repelling them. Some scientists think voids could be the ultimate architects of galactic motion, their expansion reshaping the paths of entire galaxy clusters over billions of years. But the real mystery, voids might not be as empty as they seem. Hidden within these ghostly expanses could be traces of dark energy, the enigmatic force accelerating the universe's expansion. Some theories suggest voids are where dark energy flexes its muscles, stretching space-time faster than anywhere else. If true, studying these eerie blank spots could unlock secrets about the fate of the cosmos itself, whether it will end in a cold, empty whisper or rip apart in a violent Big Rip scenario. Voids also challenge our assumptions about galaxy formation. In the dense filaments of the cosmic web, galaxies cluster like cities, but at the edges of voids, astronomers find loner galaxies isolated, quiet, and strangely underdeveloped. Without the gravitational hustle and bustle of crowded cosmic neighborhoods, these galaxies grow differently, like plants starved of nutrients. Some are red and dead, aging prematurely without the gas needed to birth new stars. Others are cosmic relics frozen in time, their evolution stunted by the void's relentless hunger for expansion. Yet even in their emptiness, voids hold a peculiar beauty. They're the negative space in the universe's grand masterpiece, the silence between the notes that makes the symphony possible. Without them, the cosmic web wouldn't be a web at all, just a formless cosmic soup. Each void is a reminder that the universe isn't just built on what's there, but on what isn't. And as telescopes peer deeper into these cosmic deserts, who knows what other invisible rules we'll find lurking in the dark? Long before the first galaxies flickered to life, before stars even existed, the universe held a secret code, a pattern so faint it was written in whispers of heat smaller than a single atom. These were quantum fluctuations, microscopic ripples in the fabric of spacetime itself, and they carried the blueprint for everything we see today. Imagine blowing up a balloon with tiny, invisible dots drawn on its surface. As the balloon expands, those marks stretch into vast, intricate patterns. That's exactly what happened to those primordial fluctuations during the Big Bang's explosive growth spurt. The proof is etched across the sky in faint, ghostly light, the cosmic microwave background, or CMB. This afterglow of creation, discovered by accident in 1965, is like a baby picture of the universe taken when it was just 380,000 years old. And here's the astonishing part. If you look closely at the CMB's temperature variations, those patches where the ancient light is slightly warmer or cooler, you're staring directly at the seeds of the cosmic web. Those subtle hot and cold spots, they map perfectly to where galaxies cluster today, revealing how gravity sculpted the universe's largest structures from subatomic beginnings. But how could something so small dictate something so vast? The answer lies in dark matter's relentless pull. Those early density variations, regions where particles happened to clump a fraction more, became gravitational wells, trapping dark matter like cosmic potholes. Over billions of years, gas followed, collapsing into these invisible scaffolds, igniting stars and birthing galaxies along the filaments we now call the cosmic web. It's a staggering chain reaction. Quantum randomness in the first trillionth of a second echoes across 14 billion years, shaping galactic superclusters with pinpoint precision. The most mind-bending realization, we're seeing quantum physics play out on the grandest possible scale. The same uncertainty principle that governs electrons in atoms also set the stage for galaxy clusters millions of light-years wide. And this isn't just theory. Supercomputer simulations tracing the universe's evolution from CMB to present day recreate the cosmic web structure with uncanny accuracy. When scientists input those ancient microwave patterns, the models spit out familiar filamentary networks, proving the link between quantum seeds and cosmic architecture. Yet mysteries remain. Some fluctuations in the CMB are stronger than current physics can explain, hinting at unknown forces at work in the universe's first moments. Others align in strange, large-scale patterns that defy probability, as if some hidden hand tuned the cosmos's initial conditions. Could these anomalies point to a deeper layer of reality, multiple universes, extra dimensions, or physics beyond our grasp? Every new map of the CMB, like those from the Planck satellite, brings us closer to answers while revealing just how much we still don't understand about the universe's first breath. So next time you gaze at the night sky, remember, the glittering tapestry above you was woven by quantum chance, stretched across eternity by gravity's patient hand. The cosmic web isn't just a structure, it's a frozen echo of the universe's infancy, a story written in the afterglow of creation itself. And with each new discovery, we're deciphering another line of that ancient cosmic code. Deep in the cosmic shadows, an invisible force wages a silent war against gravity itself. Dark energy, the universe's most enigmatic player, doesn't just nudge galaxies apart. It's actively reshaping the cosmic web's grand design. Picture a tug of war between two cosmic titans. On one side, dark matter's relentless gravity weaving galaxies into filaments, and on the other, dark energy stretching space itself like hot taffy, accelerating the expansion of the vast voids between them. This battle dictates the fate of everything we see. Here's the paradox: the same force that's tearing the cosmos apart also reveals its hidden architecture. As dark energy pushes voids to expand faster, it stretches the cosmic web's filaments thinner like threads pulled taut. Galaxies along these threads cling tighter, their local gravity resisting the cosmic tide. But in the voids, where matter is scarce and gravity's grip weakens, dark energy reigns supreme. These empty regions balloon outward at speeds that defy intuition, some growing so fast they create void shells, expanding walls of space that shunt galaxies toward denser filaments in a slow-motion tidal dance. The fingerprints of this struggle are everywhere. Look at galaxy clusters at the intersections of filaments. They're denser, hotter, and more chaotic than ever before, squeezed by the web's tightening knots. Meanwhile, isolated galaxies at the edges of voids drift like abandoned ships, their star formation stifled as dark energy drains the gas clouds they need to survive. Astronomers call this cosmic isolation syndrome, where galaxies starved of cosmic connections age prematurely, their stellar nurseries shutting down under the void's relentless expansion. But dark energy doesn't just stretch space, it rewrites time. Light traveling across growing voids gets stretched to redder wavelengths, a phenomenon called the integrated Sachs-Wolf effect. This subtle shift in the cosmic microwave background's temperature map reveals where dark energy's grip is strongest, painting an X-ray-like image of the cosmic web's tension points. It's as if the universe left us breadcrumbs in the afterglow of the Big Bang, clues to decode its ultimate fate. The strangest twist: dark energy might not be acting alone. Some theories suggest it collaborates with the cosmic web's own structure, using filaments as cosmic funnels to amplify its effects. Imagine pouring water through a network of pipes. The narrower the channel, the faster the flow. Similarly, dark energy could exploit the web's geometry, accelerating expansion more efficiently along certain pathways while gravity fights a losing battle in the densest nodes. Yet for all its power, dark energy is a latecomer to the cosmic stage. For billions of years, dark matter's gravity dominated, building the web's filaments and clusters. Only when the universe reached about half its current age did dark energy overtake gravity's pull, triggering the accelerating expansion we see today. Now we're witnessing the tipping point, a cosmic regime change where the fate of the web hangs in the balance. Will filaments eventually snap under the strain, scattering galaxies into an ever-cooling void? Or will dark matter's glue hold fast, preserving pockets of structure in an otherwise unraveling universe? Every observation, from galaxy surveys to gravitational wave detectors, brings us closer to answering the ultimate question: who wins the tug of war that shapes existence itself? Somewhere in the vast stretches between galaxies, an entire universe's worth of matter has vanished without a trace. Not dark matter, this is the ordinary, run-of-the-mill stuff that makes up planets, stars, and even us. Scientists call it the missing baryon problem, and it's one of the most baffling gaps in our cosmic ledger. Here's the math. Based on the Big Bang's chemical recipe, there should be twice as much normal matter in the present-day universe as we've actually found. That's like baking a cake with all the right ingredients, only to slice it open and discover half the flour somehow disappeared. So where did it all go? The answer lies in the cosmic web's hidden highways, the thin, scorching filaments of gas stretching between galaxies. This isn't the dense stuff of nebulae. It's a ghostly, million-degree plasma so diffuse that a coffee mug's worth would contain just a single atom. Picture steam rising from a boiling pot, only stretched across millions of light years. For decades, this gas was undetectable, its heat radiating in X-rays too faint for older telescopes to catch. But recent breakthroughs reveal it's been hiding in plain sight, woven into the web's very fabric. How do you hunt for something that barely interacts with light? Astronomers turn to cosmic trickery. When light from distant quasars, supermassive black holes blazing like intergalactic lighthouses, passes through these filaments, certain wavelengths get absorbed. It's like holding a stained glass window up to the sun and seeing which colors the glass filters out. Each absorption line is a fingerprint, revealing the presence of specific elements. Oxygen, in particular, leaves a telling mark in the ultraviolet spectrum, acting as a tracer for the web's elusive gas. But the mystery deepens. Even after accounting for these discoveries, the numbers still don't quite add up. Some theorists speculate that the missing baryons might be hiding in an even stranger form: warm-hot intergalactic medium, or WIM. This gas isn't just hot, it's in a bizarre in-between state, too energetic to form dense clouds but too cool to glow brightly in X-rays. Detecting it requires piecing together faint clues, like mapping a city's sewer system by listening for echoes in the pipes. The stakes are higher than just balancing the cosmic books. This missing matter holds the key to understanding how galaxies grow. Filaments act as pipelines, funneling gas into galactic hubs where it ignites new stars. Without them, galaxies would starve, their star factories shutting down within a few billion years. And there's another twist: some of this gas might be primordial, untouched since the Big Bang itself, a time capsule of the universe's raw ingredients before stars polluted the cosmos with heavier elements. New telescopes like the European Space Agency's Athena X-ray Observatory are poised to revolutionize the hunt. Designed to detect the faintest X-ray whispers, Athena could finally catalog the Webb's hidden reservoirs, turning theoretical predictions into observable reality. Until then, the missing baryons remain both a cosmic embarrassment and a tantalizing frontier, proof that even the ordinary can become extraordinary when it slips into the shadows of the universe's grand design. At the crossroads of the cosmic web's filaments, where dark matter threads knot together like tangled spider silk, something extraordinary happens. These intersections become gravitational hotspots, pulling in galaxies by the thousands to form the universe's grandest metropolis's galaxy clusters. Imagine a bustling city where skyscrapers are entire galaxies, each one a swirling island of billions of stars, all bound together by invisible forces. That's the reality of places like the Virgo cluster, a sprawling hub located just 54 million light-years away, making it our own galactic neighborhood's most massive gathering. Within Virgo's grasp, over 2,000 galaxies swirl in a slow-motion dance, from majestic spirals with arms like spinning pinwheels to ancient, featureless ellipticals that glow with the dull embers of aging stars. But here's what's truly wild. Despite their numbers, these galaxies aren't scattered randomly. They're organized, stacked along filaments that funnel them toward the cluster's heart, where an immense elliptical galaxy named Messier 87 waits like a cosmic monarch. At its center, a supermassive black hole weighing 6.5 billion suns devours matter, spewing jets of energy so powerful they stretch for thousands of light years. This isn't just chaos, it's controlled chaos. The galaxies in Virgo move at terrifying speeds, some exceeding 2 million miles per hour, yet they rarely collide. That's because space is vast, and even in a crowded cluster, galaxies slide past each other like cars on an endless freeway. But when they do interact, the results are spectacular. Tidal forces rip streams of stars into glowing bridges, while gas clouds compressed by the violence ignite bursts of new star formation. Some galaxies get stripped bare, their gas stolen away to float as a diffuse haze between the cluster's members. What holds this frenzy together? The answer lies in the cluster's hidden skeleton, a sea of dark matter so dense its gravity bends light like a funhouse mirror. This invisible scaffold keeps the galaxies from flying apart, while superheated gas trapped in the cluster's grip glows in X-rays at temperatures over 100 million degrees. That gas is the cluster's lifeblood, a reservoir of raw material for future stars, but also a record of the cluster's violent past. Ripples in the gas reveal ancient collisions like bruises on an old fighter, telling the story of how this metropolis grew by swallowing smaller groups of galaxies whole. And Virgo is just one of many. Across the observable universe, clusters mark the Webb's busiest intersections, each one a time capsule of cosmic evolution. Some, like the distant El Gordo cluster, are so massive they warp space-time around them, creating natural telescopes that magnify galaxies far behind them. Others, like the Bullet cluster, showcase the eerie separation of dark matter from normal matter during collisions, proof that dark matter isn't just an idea, but a tangible, ghostly presence shaping the cosmos. These knots in the web aren't just endpoints, they're waypoints in a grand journey, where galaxies gather before being funneled deeper into the universe's largest structures. But here's the twist: clusters aren't static, they grow. Filaments pump fresh galaxies into them like rivers feeding a lake, while dark energy tugs at their edges, trying to tear them apart. In the end, their fate depends on a cosmic tug-of-war, one that's been raging for billions of years and will continue until the universe itself runs cold. So when you look at a galaxy cluster, you're not just seeing a snapshot. You're witnessing a moment in an epic saga where gravity builds, dark energy erodes, and galaxies become mere passengers on the currents of the cosmic web. Hidden in the vast cosmic tapestry lies a structure so enormous it challenges our very understanding of the universe's limits, the Sloan Great Wall. Stretching an almost unimaginable 1.4 billion light-years across, this colossal filament of galaxies dwarfs everything in its path, a behemoth that makes even galaxy clusters look like mere specks of dust. Discovered in 2003 by astronomers mapping the cosmos with the Sloan Digital Sky Survey, this wall isn't just big, it defies the rules of how matter should be distributed on the grandest scales. Picture a river of galaxies so wide that light, traveling at 671 million miles per hour, would take over 1 billion years to cross from one end to the other. That's the Sloan Great Wall, not a solid barrier, but a dense network of superclusters, dark matter, and intergalactic gas woven into a single, sprawling ribbon. It's like spotting a mountain range from space, only to realize it spans an entire continent. Even more astonishing, this structure isn't alone. Similar walls, like the Hercules Corona Borealis Great Wall, stretch across the cosmos, hinting at a pattern we're only beginning to grasp. But here's where things get controversial. According to our best cosmological models, the universe should look roughly the same no matter where you look, a principle called the cosmological principle. Structures shouldn't grow beyond a certain scale without breaking the rules of how gravity and cosmic expansion interact. Yet the Sloan Great Wall laughs at those limits. It's like finding a single skyscraper in the middle of an endless plain, an anomaly that shouldn't exist. Some theorists argue it might be a statistical fluke, a chance alignment of smaller filaments. Others whisper about flaws in our understanding of dark matter's behavior, or even the possibility of exotic physics left over from the Big Bang. The real puzzle isn't just its size, it's how such a thing could form in the first place. Gravity works slowly, and in the 14 billion years since the universe began, there shouldn't have been enough time for matter to clump together on this scale. Computer simulations struggle to recreate it, often producing cosmic webs that look far more uniform. One radical idea suggests these great walls might be scars from the universe's infancy, primordial ripples frozen into the fabric of spacetime, where dark matter pooled like water in a ditch, dragging galaxies into its grip over eons. Yet for all its mystery, the Sloan Great Wall isn't just a scientific headache, it's a Rosetta Stone for decoding the cosmic web's largest patterns. By studying its structure, astronomers can trace how dark matter's gravity sculpts the universe's skeleton and whether dark energy's expansion leaves fingerprints in these megastructures. Future telescopes like the Vera C. Rubin Observatory aim to map even more of these cosmic giants, probing whether they're rare oddities or part of a hidden architecture we've only glimpsed. What's certain is this: the Sloan Great Wall forces us to rethink what's possible. It's a reminder that the universe doesn't always play by the rules we've written, and that the cosmic web's grandest designs might still be waiting to be uncovered. Beneath the searing heat and ghostly tendrils of the cosmic web's filaments, another invisible force silently pulses, a whisper-thin magnetic field stretching across millions of light-years. These cosmic threads aren't just highways for matter, they're threaded with magnetism so faint it defies detection, yet powerful enough to sculpt galaxies in ways we're only beginning to understand. Unlike the bar magnets of a child's science experiment, these fields don't come from iron cores or electric currents. They're primordial, woven into the fabric of the universe itself during its earliest moments, then amplified by the turbulent motions of gas flowing through the web's veins. The hunt for these elusive magnetic fields is like trying to hear a whisper in a hurricane. Traditional telescopes see nothing; these forces leave no visible trace. But radio telescopes, tuned to the universe's faintest signals, catch the subtle clues. As charged particles spiral along magnetic field lines, they emit a unique radio glow called synchrotron radiation. It's the same phenomenon that lights up the jets of black holes, only here it's diffused across unimaginable distances, a faint hum against the cosmic background. The LOFAR array in Europe, with its thousands of antennas, has become a master at decoding these whispers, revealing filaments where magnetism is strong enough to nudge cosmic rays, yet so delicate it wouldn't budge a compass needle on Earth. Why does this matter? Because magnetism might be the cosmic web's silent architect. Gas flowing along filaments isn't just pulled by gravity, it's channeled by these fields like water diverted by underground pipes. In galaxy clusters, magnetic fields prevent gas from collapsing too quickly, slowing star formation and keeping galactic neighborhoods from burning out too soon. They might even solve the cooling flow problem, a decades-old mystery about why galaxy clusters don't condense into stars as rapidly as physics predicts. Magnetism could be the cosmic brake pedal, regulating how fast the universe turns gas into light. The implications get stranger. Some theorists suggest these fields guide cosmic rays, particles traveling near light speed along filaments like interstellar highways. Without magnetism's invisible rails, these rays might scatter randomly, never reaching the galaxies where they could influence cloud formation or even atmospheric chemistry on planets. There's even wilder speculation. If magnetic fields permeate the entire web, they could be relics from the Big Bang itself, frozen into space-time during inflation like wrinkles in a stretched sheet. That would make them time capsules, preserving secrets from the universe's first trillionth of a second. Yet for all their influence, these fields remain maddeningly elusive. They're 1,000 times weaker than Earth's magnetic field, and their patterns are chaotic. Some filaments show tight, spiral-shaped fields, while others have open, comb-like structures. New instruments like the Square Kilometre Array, set to become the world's most sensitive radio telescope, aim to map them in unprecedented detail. What they find could rewrite textbooks, proving that the cosmic web isn't just a scaffold for matter. It's a living, magnetic tapestry, quietly shaping the evolution of everything it touches. At the heart of the galaxy Messier 87, a monster awakens. Its supermassive black hole, weighing as much as 6.5 billion suns, doesn't just devour matter, it retaliates. From its poles, twin jets of plasma scream into the void at nearly the speed of light, stretching over 5,000 light-years across the cosmos. These aren't just cosmic fireworks, they're wrecking balls, slamming into the delicate filaments of the cosmic web with enough force to reshape entire galactic neighborhoods. The collision is like a fire hose blasting a spider's silk. The jet's supercharged particles, accelerated by the black hole's immense magnetic fields, carve through the web's gaseous filaments, heating them to temperatures hotter than the cores of stars. Shockwaves ripple outward, stirring the tranquil flow of intergalactic gas like a spoon through honey. In some regions, the jet's energy is so intense it halts star formation entirely, stripping galaxies of the raw materials they need to birth new suns. Yet paradoxically, in others, the same violence triggers bursts of creation, compressing gas clouds until they collapse into fiery stellar nurseries. M87's jet isn't unique. Across the universe, supermassive black holes act like cosmic regulators, their outbursts balancing the web's growth. When too much gas funnels into a filament, the central black hole in a galaxy cluster can switch on, blasting away the excess like a pressure valve. This feedback loop keeps the web from growing too dense, preventing galaxies from burning through their fuel too quickly. But there's a dark side. In smaller galaxies, these jets can be apocalyptic, blowing away a galaxy's entire gas reservoir in one catastrophic eruption, leaving it a sterile wasteland of aging stars. Recent X-ray observations reveal something even stranger. These jets don't just fade into the void, they etch bubbles into the web structure, cavities of scorched gas that persist for hundreds of millions of years. Inside these bubbles, magnetic fields twist and amplify, creating cosmic accelerators that hurl particles across intergalactic space. Some scientists believe these bubbles could be the source of mysterious ultra-high energy cosmic rays, particles with energies so extreme they defy explanation. The dance between black holes and the cosmic web is one of destruction and creation, chaos and order. Without these jets, the web might clot into dense knots, stranding galaxies in isolated pockets. But with them, the universe maintains a fragile equilibrium where violence begets structure and catastrophe writes the rules of cosmic design. As we peer deeper into the storm, we're left with a haunting question. Are black holes the architects of the web's beauty or the agents of its unmaking? The cosmic web's filaments should be teeming with dwarf galaxies, tiny, faint collections of stars that outnumber their larger cousins by the thousands. According to supercomputer simulations of dark matter's behavior, every massive galaxy like the Milky Way should be surrounded by swarms of these dwarfs, each one clinging to the web's threads like fireflies in a vast, invisible net. But when astronomers peer into the night sky, they find a glaring mismatch. Only a fraction of the predicted dwarfs are actually there. This cosmic case of missing matter isn't just a counting error. It's a crisis that could rewrite our understanding of dark matter itself. Take the Milky Way's neighborhood. Current models suggest our galaxy should host at least several hundred dwarf galaxies, yet we've only spotted about 60. Where are the rest? Some might be hiding in plain sight, their stars so sparse they blend into the darkness between brighter galaxies. Others could be dark galaxies, ghostly clumps of dark matter with almost no stars at all, floating undetected like ships lost in fog. But even accounting for these possibilities, the numbers still don't add up. The discrepancy is so stark it's earned a name, the missing satellites problem, and it's one of the most persistent puzzles in modern astrophysics. One clue lies in how dark matter behaves. The most widely accepted model, called cold dark matter, assumes these particles move sluggishly, clumping easily under gravity's pull. But if dark matter is slightly warmer, or interacts in ways we haven't accounted for, it might not form as many small-scale structures. Imagine stirring sugar into coffee. Cold dark matter would leave gritty lumps at the bottom, while warmer versions might dissolve more evenly, leaving fewer detectable clumps. Alternative theories like self-interacting dark matter or fuzzy dark matter attempt to tweak the rules, suggesting these particles might bounce off each other or behave like quantum waves, smoothing out the smallest dwarf galaxy seeds before they can grow. Yet there's another twist. The dwarfs we have found aren't where they should be. Simulations predict they'd orbit randomly, like bees around a hive. Instead, they're locked into an unnervingly flat plane around the Milky Way, circling like cars on a racetrack. This plane of satellites defies standard dark matter models, hinting that either our galaxy's history is stranger than we thought, or that dark matter's gravity works differently on small scales. Some astronomers argue these dwarfs might be cosmic newcomers, captured by the Milky Way during a long-ago collision with another galaxy, their orbits frozen in place like debris from a car crash. Others propose the plane is an illusion, a chance alignment that will dissolve as we discover more dwarfs in the coming years. The hunt for answers is pushing telescopes to their limits. Projects like the Vera-C, Rubin Observatory's legacy survey of space and time, are scanning the skies with unprecedented sensitivity, poised to uncover dwarfs so faint they've been virtually invisible until now. Meanwhile, radio telescopes like Meerkat in South Africa are searching for the faint glow of hydrogen gas in these elusive galaxies, tracing their presence even when stars are scarce. Every new discovery tightens the noose around dark matter's mysteries, forcing us to ask, are we missing something fundamental about the universe's scaffolding, or is the cosmic web hiding more secrets than we ever imagined? One thing's certain, the missing dwarfs aren't just a footnote in cosmic history. They're the key to unlocking dark matter's true nature, and with it, the fate of the web that binds us all. Whether they are hiding in the shadows or never existed at all, their absence speaks volumes, a silent challenge to everything we think we know about the universe's hidden architecture. Deep in the light of ancient quasars, a ghostly pattern emerges. a forest of shadows etched into the rainbow of starlight. These are the Lyman alpha lines, the spectral fingerprints of hydrogen gas clouds strewn across the universe like dew on a spider's web. When a quasar's brilliant beam journeys through billions of light years to reach us, it doesn't travel untouched. Countless filaments of the cosmic web siphon away specific wavelengths, leaving behind a barcode of darkness that tells the story of everything it passed through along the way. The phenomenon works like sunlight filtering through a stained glass window, except instead of colored panes, the light encounters clouds of hydrogen gas. Each cloud absorbs a tiny portion of the quasar's ultraviolet light at a precise wavelength corresponding to the Lyman alpha transition, an electron jump unique to hydrogen atoms. As the universe expands, these absorption lines get stretched to longer wavelengths, creating a forest of lines across the spectrum. The closer the gas cloud is to us, the redder its shadow appears. The result, a single quasar's light can reveal hundreds or even thousands of these lines, each one a snapshot of hydrogen distribution at a different point in cosmic history. What makes the Lyman alpha forest revolutionary is its sheer scope. Traditional galaxy surveys map the universe's structure by spotting bright objects, but that's like mapping a forest by only counting the tallest trees. The Lyman alpha method captures the undergrowth, the diffuse gas between galaxies that makes up the cosmic web's true bulk. By analyzing the density and spacing of these absorption lines, astronomers reconstruct the web's three-dimensional architecture, tracing filaments too faint to see directly. Some lines cluster tightly, revealing dense knots where filaments intersect. Others spread thinly, marking the vast, empty voids between the web's strands. The real magic happens when you compare these shadows to dark matter maps. Supercomputer simulations predict how dark matter's gravity should distribute hydrogen gas, and the Lyman alpha forest provides the observational proof. The match is uncanny. Wherever simulations place a dark matter filament, quasar light shows a corresponding thicket of hydrogen absorption. This synergy between theory and observation has cemented the forest as one of our most powerful tools for probing the web's hidden geometry. Yet the forest holds deeper secrets. The width of each absorption line betrays the gas's temperature and motion. Narrow lines mean cold, calm clouds, primordial gas untouched since the Big Bang. Broad, fuzzy lines suggest turbulence, heated by supernova shockwaves or the gravitational pull of passing dark matter clumps. Some lines even split into multiple peaks, evidence of gas flowing along filaments like water through a canyon. By reading these subtle variations, scientists measure the web's dynamic processes, from galactic winds ejecting matter into the voids to the gentle infall of gas feeding growing galaxies. Recent breakthroughs have turned this technique on its head. Instead of relying on distant quasars, astronomers now use the Lyman alpha forest to map nearby structures, including our own cosmic web neighborhood. By observing thousands of background galaxies, not just quasars, projects like the Sloan Digital Sky Survey have stitched together a local map of filaments, revealing highways of gas that connect the Virgo cluster to other galactic superstructures. The forest has even hinted at the missing baryons problem, with some studies suggesting the web's diffuse gas could account for the universe's unlocated normal matter. But the most tantalizing clues lie in the forest's rarest features, so-called damped Lyman alpha systems, clouds so thick they completely block quasar light at specific wavelengths. These are the web's reservoirs, gas-rich nurseries that could birth future galaxies. Some may even be proto-galaxies caught in the act of formation, their hydrogen not yet lit by stars. As telescopes like the James Webb Space Telescope peer deeper into these shadows, they're uncovering a universe far richer and more intricate than anyone predicted. A cosmos woven not just with galaxies, but with the invisible threads that bind them all together. Peering into the depths of space isn't just about distance, it's about time. Every filament of the cosmic web we observe is a snapshot of the universe's past, a frozen moment in an epic saga of structure and chaos. Look far enough and you're not just seeing the web's threads, you're witnessing its infancy, a time when galaxies were still taking their first steps into the cosmic dance. Take a filament 12 billion light-years away. The light we see today left its source when the universe was a mere 2 billion years old, a fraction of its current age. Back then, the web looked wildly different, not sleek and defined like today's sprawling highways, but a frayed, tangled mess of gas and dark matter, still knitting itself together. Galaxies along these early filaments were smaller, hotter, and bursting with star formation like sparks along a fuse. Compare that to the mature filaments near us today, where galaxies move in stately orbits, their star-making factories quieter, their structures refined by billions of years of gravitational choreography. The difference is striking. Modern filaments are like well-paved interstates with galaxies gliding smoothly along gravitational grooves, but ancient filaments, they're more like muddy backroads full of potholes and detours. Gas clouds collide violently, triggering frenzied bursts of star birth. Dark matter clumps haven't yet merged into smooth streams, leaving the web's scaffolding lumpy and uneven. In some regions, filaments haven't even fully formed, just scattered knots of matter waiting to be connected by gravity's slow pull. This cosmic time machine isn't just about nostalgia. By comparing ancient and modern filaments, astronomers catch the web in the act of growing up. They see how turbulence settles into order, how chaotic gas flows become organized rivers feeding galaxies. They even spot the fingerprints of dark energy's influence. Those early filaments are packed tighter, their galaxies closer together before dark energy began stretching the universe apart. The James Webb Space Telescope has become our ultimate time-traveling tool, capturing filaments so distant their light predates Earth itself. In one recent study, Webb revealed a filament from just 800 million years after the Big Bang, a thread so young it's barely more than a wisp of hydrogen, dotted with galaxies still fresh from formation. Nearby, the Hubble Space Telescope maps mature filaments, their galaxies settled into the Webb's rhythm. Side by side, these images tell a story 14 billion years in the making, a tale of how randomness becomes structure and chaos gives way to cosmic order. But the past holds surprises. Some early filaments bend the rules, appearing more massive than modern theory predicts. Others show galaxies moving too fast, as if gravity alone couldn't explain their motion. These outliers might hint at unknown forces at work in the young universe, extra dark matter, primordial magnetic fields, or even relics from inflation's first moments. Every anomaly is a clue, a whisper from a time when the universe was still figuring out what it wanted to be. So when astronomers gaze down the Webb's timeline, they're not just cataloging the past. They're testing the laws of physics themselves, watching how those laws play out over spans no human experiment could ever match. The cosmic web doesn't just connect galaxies, it bridges epochs, letting us witness the universe's greatest transformation firsthand. And with each new observation, we get a little closer to understanding how something so vast, so ancient, and so impossibly complex could emerge from the simplicity of the Big Bang's afterglow. Trillions of ghostly particles pass through your body every second, silent, weightless, utterly undetectable. These are neutrinos, the universe's most elusive travelers, born in the hearts of stars, supernova, and even the Big Bang itself. With no electric charge and nearly no mass, they slip through planets like sunlight through glass, rarely interacting with anything in their path. But what if these cosmic phantoms aren't just passing through the cosmic web? What if they're subtly shaping it? Neutrinos move at nearly the speed of light, their paths barely bent by gravity. Yet over billions of years, even their whisper-thin mass might leave a mark. Simulations suggest that as neutrinos stream through dark matter filaments, their collective gravity, though infinitesimal, could nudge gas particles, altering how matter accumulates along the web's threads. It's like a breeze so gentle you can't feel it, yet given enough time, it might sculpt sand dunes. In the early universe, where filaments were still condensing, this effect could have been crucial, steering gas into denser channels where galaxies would later form. The challenge is catching them in the act. Neutrinos barely interact with matter, making them astronomically hard to detect. That's where experiments like IceCube come in. Buried deep in the Antarctic ice, this observatory doesn't look for neutrinos directly. It hunts for the fleeting blue glow of charged particles created when a neutrino, against all odds, collides with an atom in the ice. These rare collisions act like cosmic breadcrumbs, hinting at where high-energy neutrinos originated. Already, IceCube has traced some back to violent events like Blazar's supermassive black holes spearing the cosmos with particle jets, proving that these ghostly particles carry information across the Webb. But the real breakthrough came when scientists matched neutrino data with maps of the cosmic web. Some high-energy neutrinos seem to arrive from directions where multiple filaments intersect, as if the densest knots in the web are also neutrino hotspots. One theory suggests that shockwaves from colliding galaxy clusters, like those in the Bullet cluster, could accelerate particles to extreme energies, turning filaments into colossal neutrino factories. If true, neutrinos might not just be passive travelers. They could be cosmic byproducts of the Webb's most violent construction sites. The plot thickens when you consider relic neutrinos, those left over from the Big Bang. These ancient particles, cooled by the universe's expansion, might still drift through the Webb like a faint cosmic fog. Though individually feeble, their combined mass could warp spacetime on the largest scales, subtly bending the paths of light from distant quasars. Some cosmologists think relic neutrinos might even contribute to dark matter's hidden bulk, a notion that could rewrite our understanding of the Webb's scaffolding. Yet for all their mystery, neutrinos hold a tantalizing promise. They're messengers from places light can't reach. Black holes, the hearts of supernova, even the universe's first seconds, all are opaque to telescopes but transparent to neutrinos. Future detectors like the planned IceCube Gen 2 aim to catch even fainter signals, painting a neutrino map of the cosmic web. Imagine seeing the universe not in starlight but in the shadows of these phantoms, a hidden blueprint of how everything connects. So the next time you look up at the night sky, remember, you're not just standing under a tapestry of stars. You're swimming in an ocean of ghosts, their silent whispers shaping the cosmos in ways we're only beginning to hear. Stretching across nearly a tenth of the observable universe, the Hercules Corona Borealis Great Wall isn't just large, it's impossibly large. This colossal arc of galaxies, discovered in 2013, spans over 3 billion light-years, a structure so vast it could fit 15,000 Milky Ways end to end. But its size isn't the only thing that defies logic. Its very existence challenges one of cosmology's most sacred principles, the idea that on the largest scales, the universe should look roughly the same in all directions. At first glance, the giant arc seems like just another filament in the cosmic web, a dense thread of galaxies woven through the void. But when astronomers measured its staggering dimensions, the numbers didn't add up. According to the cosmological principle, there's a fundamental limit to how big structures should grow. Matter should distribute fairly evenly across cosmic distances, like sprinkles mixed into batter. Yet here's a wall that breaks that rule by a factor of 3, a cosmic Everest towering over theoretical predictions. The controversy hinges on a question as old as astronomy itself. Is this structure real or a trick of perspective? Detecting patterns in randomness is a quirk of human perception. We see faces in clouds and animals in the stars. Could the giant arc be a statistical fluke, a chance alignment of unrelated galaxies strung together like false constellations? Some simulations suggest yes, showing that even in a perfectly uniform universe, occasional large-scale clusters can appear by accident. Yet the arc's supporters point to its eerie symmetry. Its galaxies aren't just randomly clustered, they trace a curve so precise it resembles a gravitational shockwave frozen in time. Then there's the puzzle of its formation. Gravity moves at the speed of light, and in the 14 billion years since the Big Bang, there simply hasn't been enough time for matter to clump together on this scale. Unless, of course, our understanding of dark matter's behavior is incomplete. Some theorists propose exotic solutions, primordial black holes seeding early overdensities, or dark matter particles with unusual interactions that accelerated cosmic scaffolding. Others whisper about cosmic strings, hypothetical defects in space-time left over from the universe's birth, warping the distribution of matter like scars on a balloon. The debate grows hotter when you consider the ark's neighbors. It isn't alone in challenging the cosmological principle. Nearby lies the Sloan Great Wall, and beyond it, the Boss Great Wall, each stretching over 1 billion light-years. Together, they hint at a hierarchy of structures far grander than our models predicted, like finding a series of mountain ranges where maps showed only flat plains. Are these anomalies outliers or evidence of a deeper pattern woven into the cosmic web? New telescopes might finally settle the argument. The Euclid Space Observatory, with its razor-sharp infrared vision, is mapping the ark's 3D structure to determine whether its galaxies are truly bound or just a line-of-sight illusion. Meanwhile, next-generation radio arrays like the Square Kilometre Array could detect faint hydrogen gas between the ark's galaxies, revealing whether they're connected by invisible filaments or floating independently. Every observation tightens the noose around this cosmic conundrum. What's at stake isn't just the fate of one strange structure, it's the foundation of modern cosmology itself. If the giant arc is real, it could force us to rewrite the rules of how the universe grows, or even rethink the nature of dark energy's expansion. If it's an illusion, it's a reminder of how easily the cosmos can deceive us, hiding its truths behind layers of statistical noise. Either way, this enigmatic arc reminds us that for all our knowledge, the universe still holds cards it hasn't revealed, and the cosmic web's greatest secrets might be written in scales we're only beginning to see. Somewhere beyond the edge of everything we can see, something massive is pulling at our universe like an invisible hand. Hundreds of galaxy clusters, each containing thousands of galaxies, are streaming through space at over 1 million miles per hour in the same direction, as if caught in a cosmic current no one can explain. Astronomers call this phenomenon dark flow, and it's one of the most baffling mysteries in modern cosmology. These clusters aren't just drifting randomly, they're being tugged toward a point so distant it lies beyond the observable horizon of our universe. The discovery came when scientists mapped the motion of galaxy clusters using the cosmic microwave background as a reference. Imagine trying to measure a river's current by watching how leaves drift across its surface. That's essentially what researchers did, using the CMB's subtle temperature shifts to track clusters moving en masse against the universe's expansion. The findings were staggering: over 700 clusters, some billions of light-years apart, all moving toward the same patch of nothingness. Gravity from known structures couldn't explain it. Even dark energy's push wouldn't create this kind of coordinated motion. So what's pulling them? One radical idea suggests the culprit might lie outside our universe entirely. In multiverse theories, our cosmos could be one bubble among countless others in a frothing sea of space-time. If a neighboring bubble universe passed close enough to ours, its gravitational influence might create this dark flow, like a magnet tugging iron filings through a sheet of paper. The thought is as thrilling as it is unsettling, evidence that our universe isn't alone, that beyond the veil of our observable reality, other cosmic realms brush against our own, leaving fingerprints in the motion of galaxies. Critics argue the data could be flawed, a trick of measurement or incomplete maps of galactic motion. But newer studies, like those from the Planck satellite, have only deepened the mystery. The flow persists, and its preferred direction aligns eerily with other cosmic anomalies, cold spots in the CMB. voids that seem too large, even the Great Attractor's unexplained pull. Together, they hint at a grand asymmetry in the universe, a tilt in the cosmic fabric that defies our standard models. If dark flow is real, the implications rewrite cosmology. It could mean the Big Bang wasn't perfectly uniform, that some regions of the early universe carried more momentum, creating this lingering drift. Or it might point to pre-Big Bang physics, relics from an era before time as we know it began. Either way, the Webb's hidden currents remind us that for all we've mapped, the universe still holds forces we can't see, can't touch, and barely understand, whispers from beyond the edge of everything. The cosmic web isn't just a static skeleton, it's a bustling delivery system, a network of highways where rivers of cold gas surge toward galaxies like cosmic rain. These filaments don't merely connect galaxies, they feed them, channeling the raw materials needed to ignite new stars in a process so vast and precise it could be mistaken for a celestial irrigation system. And our own Milky Way is no exception. At this very moment, it's gulping down gas from a filament known as the Magellanic Stream, a ribbon of hydrogen stretching across the sky like a phantom river. Here's how it works. As gas flows along these filaments, gravity pulls it toward denser regions, galaxy clusters, or massive spirals like ours. But this isn't just any gas. It's cold, barely a few degrees above absolute zero, which makes it perfect for collapsing into stars. Unlike the scorching plasma of intergalactic voids, this cool, dense material slips through the Webb's threads like morning mist, pooling in galactic halos before spiraling inward. Picture a rainforest canopy catching moisture from passing clouds, funneling every drop toward its roots. That's what filaments do for galaxies, only on a scale where the raindrops could birth entire solar systems. The Milky Way's fountain is a stunning example of this cycle in action. Near the galactic center, supernova and violent stellar winds blast gas outward at millions of miles per hour, creating a halo of hot, ejected material. But gravity doesn't let it escape forever. Over millions of years, this gas cools, condenses, and falls back toward the disk in a shimmering downpour, a phenomenon astronomers call a galactic fountain. Some of this returning rain might even originate from ancient filaments, recycled through the galaxy's turbulent atmosphere like water evaporating and reforming into clouds. But the real magic happens when this gas reaches the Milky Way's spiral arms. There, compressed by shockwaves and collisions, it fragments into dense clouds, each one a potential nursery for thousands of stars. Without this steady inflow from the cosmic web, our galaxy would have run out of fuel billions of years ago, its star factories shuttered and its spiral arms fading into darkness. Yet there's a twist. Not all gas arrives peacefully. Some filaments collide with galaxies at oblique angles, sparking turbulence that can either stifle star formation or trigger bursts of it, depending on the galaxy's mood. Others bring a mix of pristine hydrogen and heavier elements forged in distant supernova, seeding galaxies with the ingredients for planets and life. The Webb doesn't just build galaxies, it seasons them, shaping their evolution with every elemental delivery. New telescopes like the Green Bank Observatory are mapping these flows in unprecedented detail, revealing filaments so delicate their gas would vanish in Earth's atmosphere, yet so vast they sustain galaxies for eons. Every thread they trace is a lifeline, a reminder that the universe doesn't just connect its structures, it nourishes them. And as we piece together this cycle of cosmic rain, we're glimpsing something profound. The Webb isn't just the universe's architecture. It's its bloodstream, floating in the depths of space 12 billion years from Earth. There's a cloud of water so massive it defies comprehension, a single filament near a quasar holding 140 trillion times all the water in Earth's oceans. This isn't just a reservoir, it's the largest deposit of water ever discovered, a cosmic ocean suspended in the threads of the cosmic web. The numbers alone are staggering, enough water to fill every drop of every sea on a million Earths, all drifting in the darkness as vapor. bound by gravity to an ancient strand of the universe's grand design. This watery behemoth was found wrapped around APM 08279 plus 5255, a quasar burning with the brilliance of 1,000 galaxies. Quasars are the universe's lighthouses, supermassive black holes so voracious they outshine their host galaxies, their accretion disks blazing with heat as they devour matter. And as their light pierces the cosmic web, it passes through layers of gas, dust, and in this case, an unimaginable fog of water molecules. Astronomers first spotted the cloud using the Z-spec instrument at the Caltech Submillimeter Observatory, catching the faint microwave whispers of water vapor stretched over hundreds of light years. Here's what makes this discovery so extraordinary. Water, even in space, isn't rare. It clings to comets, frosts the poles of moons, and drifts in interstellar clouds. But this Filaments reservoir exists on an entirely different scale, a relic from an era when the universe was barely 1.6 billion years old. Back then, the cosmic web was still knitting itself together, and this quasar's filament acted like a cosmic sponge, trapping primordial hydrogen and oxygen in its gravitational grip. Over eons, radiation from the quasar and nearby starbursts heated the gas, forging water molecules in a process that still churns today. But how does something this vast stay intact? The answer lies in the filament's delicate balance of forces. The water isn't a free-floating cloud. It's woven into the filament structure, held in place by dark matter's invisible scaffolding. Radiation from the quasar keeps it from cooling and collapsing into ice or stars, while the filament's sheer size, spanning thousands of light years, prevents it from dissipating into the void. It's a self-sustaining system, a celestial distillery where water vapor cycles endlessly, evaporating and recondensing under the quasar's furious glow. This discovery rewrote the rules of cosmic chemistry. Before, no one suspected the Webb's filaments could harbor such immense stores of water, let alone in regions so hostile. Quasars blast their surroundings with enough radiation to strip molecules apart, yet here water thrives. The finding hints at a hidden universality. Wherever the Webb's threads weave through the cosmos, water might follow, clinging to filaments like morning dew on a spider's silk. And if that's true, these vapor rivers could be far more common than we ever imagined, threading through the darkness in places we've yet to explore. The implications ripple outward. Water isn't just a curiosity, it's the universal solvent, the medium of life as we know it. While this particular cloud is too hot and irradiated to harbor biology, its existence proves that the cosmic web doesn't just shuttle galaxies and dark matter. It's also a conduit for the elements of life, ferrying them across the universe to where they might one day pool in calmer waters. Future telescopes, like the James Webb Space Telescope, could uncover more of these hidden reservoirs, mapping the Webb's wet veins and tracing how water journeys from the depths of space to the shores of newborn worlds. So the next time you take a sip of water, remember, the molecules in your glass might have once ridden the currents of the cosmic web, part of an ancient, invisible ocean that spans time and space. And somewhere out there, another filament might be hiding a sea vast enough to drown entire galaxies, waiting for the light of a distant quasar to reveal its secrets. Scientists have a problem. The universe is expanding, but no one can agree on how fast. This isn't just some academic debate, it's a full-blown crisis called the Hubble tension. On one side, measurements from nearby galaxies and supernovas suggest a faster expansion rate. On the other, the cosmic microwave background, the echo of the Big Bang, points to a slower one. The discrepancy isn't slight, it's a gap large enough to rewrite cosmology. But what if the answer isn't in the stars or the afterglow of creation? What if it's hidden in the dark tendrils of the cosmic web? For decades, astronomers assumed the Webb's filaments were straightforward, gravitational highways where dark matter and gas flowed predictably. But new simulations suggest these threads might be more complex, their shapes and densities varying wildly across the cosmos. Some filaments could be thicker, acting like cosmic speed bumps that subtly slow the local expansion of space. Others might be thinner, creating voids where expansion accelerates unchecked. If true, this would mean our measurements of the universe's growth aren't just about distance, they're about perspective. Depending on where you look, the Webb itself could be warping the numbers, creating pockets where expansion appears faster or slower than the cosmic average. Here's the twist: we've been mapping the Webb using incomplete data. Most expansion rate calculations assume a smooth, evenly distributed universe, a simplification that ignores the Webb's lumpy reality. Imagine trying to measure the speed of ocean currents while ignoring the shape of the seafloor. The Hubble tension might not be a flaw in our physics, but a flaw in our maps. Filaments could be hiding vast reservoirs of dark energy or unknown forms of matter that tug on space-time in ways we haven't accounted for. Some theories even suggest that dark energy itself isn't constant. It could be stronger along certain filaments, weaker in voids, a variable force woven into the Webb's very fabric. The stakes couldn't be higher. If the Webb is skewing our measurements, it means our entire cosmic yardstick is bent. The age of the universe, the fate of galaxies, even the nature of dark energy, all could shift based on how we untangle this knot. And there's tantalizing evidence this might be the case. Recent galaxy surveys show peculiar flows, large-scale motions where galaxies drift toward dense filaments as if caught in a hidden current. These flows don't match standard expansion models, but they align eerily with simulations where filaments exert extra gravitational pull. The solution might lie in next-generation telescopes. Projects like the Vera-C Rubin Observatory will map billions of galaxies, tracing the Webb's structure with unprecedented precision. By comparing these maps to expansion rate measurements, astronomers could finally see if filaments are the missing variable in the Hubble equation. Until then, the tension remains a cosmic tug-of-war between observation and theory, with the Webb's shadowy threads holding the rope. One thing's certain: the universe isn't just expanding. It's whispering secrets through the very fabric that binds it together. For billions of years after the Big Bang, the universe was a pitch-black sea of hydrogen, an era so devoid of light astronomers call it the cosmic dark ages. Not a single star flickered in the void, just an endless, silent fog of gas waiting for something, anything, to ignite the first spark. Then, like fire spreading across dry brush, light began piercing through. The cosmic Webb didn't just witness this transformation, it made it happen. Those dark matter filaments, invisible and patient, became the universe's first power lines, channeling gas into dense knots where gravity could finally crush atoms together and birth the stars that ended the darkness forever. The James Webb Space Telescope has finally caught this epoch in action. Peering back over 13 billion years, its infrared eyes have spotted some of the earliest strands of the Webb, filaments so young they're still pulling in their first galaxies. Unlike the sleek, defined threads we see today, these primordial filaments were ragged and turbulent, their gas flows chaotic as gravity struggled to bring order to the cosmos. Yet even in their infancy, they were hard at work. Webb's images reveal something astonishing. The first galaxies didn't form randomly. They lined up along these filaments like beads on a string, proof that the Webb's architecture was guiding cosmic evolution from the very beginning. What's even more remarkable is how these filaments acted as cosmic matchmakers. As gas rushed along their lengths, galaxies at their intersections collided and merged, their black holes feasting and growing into the brilliant quasars that ultimately ionized the universe. It was a chain reaction. Filaments fed the galaxies, galaxies birthed stars, and those stars flooded space with enough ultraviolet radiation to burn away the hydrogen fog, ending the dark ages in a blaze of light. Webb's spectra confirm this, showing how the earliest filaments are rich with heavy elements forged in those first stellar furnaces, their chemistry already seeding the cosmos with the building blocks of planets and life. But the real surprise came when researchers noticed something odd about these ancient filaments. They're hotter than modern ones. Supercomputer simulations reveal why. The early Webb was a violent construction site. Dark matter clumps smashed together, sending shockwaves through the gas that heated it to millions of degrees. Meanwhile, the first supermassive black holes pumped out energy like cosmic blowtorches, their radiation supercharging the filaments around them. This heat wasn't just a side effect, it was crucial. Hot gas resists collapsing into stars too quickly, preventing galaxies from burning out before they could grow large enough to sustain themselves. The filaments weren't just building the first cities of stars, they were regulating their growth, ensuring the universe didn't spend all its fuel too soon. Nowhere is this delicate balance more evident than in Webb's observations of a filament dubbed the cosmic vine, a thread of galaxies from just 800 million years after the Big Bang. This structure, which shouldn't exist according to early universe models, contains over 20 galaxies already linked by dark matter's pull. Some are churning out stars 100 times faster than the Milky Way does today, their brilliance powered by the filament's steady gas supply. Others appear stunted, their growth throttled by feedback from nearby quasars. A reminder that even then, the Webb was both creator and destroyer, giving with one invisible hand while taking away with the other. As Webb peers deeper, it's uncovering hints that some filaments might have lit up the universe earlier than we thought. A handful of galaxies now appear to have switched on barely 200 million years after the Big Bang, their existence defying expectations of how quickly cosmic structures could form. One theory suggests dark matter might have clumped faster than predicted, jump-starting the Webb's assembly. Another posits that mysterious, dark stars, hypothetical objects powered by dark matter annihilation, could have provided the first flickers before true stars took over. Whatever the answer, each discovery proves one thing. The cosmic web didn't just shape galaxies, it wrote the rules for how light would conquer the darkness, setting the stage for everything that followed. So when you gaze at the night sky, remember, every star, every galaxy, every glimmer you see exists because an invisible network of filaments worked in the shadows, patiently gathering the scraps of creation into the glittering universe we call home. And thanks to Webb, we're finally reading that origin story in the Webb's own words, written in starlight, gas, and the echoes of cosmic dawn. Deep in the cosmic abyss of the Boots void, a 330 million light-year emptiness so vast it could swallow thousands of Milky Ways without a trace, there's a single defiant speck of light. This is ESO 46136. A lonely galaxy drifting through what astronomers call the Great Nothing, a region of space so desolate that its nearest galactic neighbor might as well be on the other side of the universe. If the cosmic web is a bustling metropolis of interconnected filaments, the Boots Void is its Antarctica, barren, isolated, and brutally inhospitable. Yet here, against all odds, this galaxy persists like a solitary lantern in an endless night. How does ESO 46136 survive in a place where galaxies simply shouldn't exist? The answer might lie in its peculiar appearance. Unlike the majestic spirals or glowing ellipticals we're used to, this galaxy is a faint, irregular smudge, a cosmic castaway stripped of the gas and dust needed to spark new stars. Observations suggest it's what astronomers call a dwarf transitional galaxy, a relic from an earlier era clinging to the last dregs of its star-forming material. Its faint glow hints at a turbulent past. Perhaps it was once part of a larger group, torn away by gravitational tides and flung into the void, left to wander the cosmic wilderness alone. But the real mystery isn't just how it got here, it's how it hasn't faded into oblivion. In a void, galaxies are starved of the fresh gas that filaments normally funnel in from the Webb. Without it, they burn through their reserves, sputter out, and fade into darkness. Yet ESO 46136 still flickers with signs of life. One theory suggests it might be a galactic cannibal, surviving by consuming smaller companions that strayed too close. Another posits that it's hoarding ancient gas clouds, eking out star formation at a glacial pace. A single stellar birth every few million years, just enough to keep the lights on. The most tantalizing possibility, the boot's void isn't as empty as it seems. Hidden beneath the darkness could be a phantom filament, a thread of dark matter too sparse to attract much gas but dense enough to anchor this lone galaxy. Like a spider surviving on a single strand of silk in an otherwise barren room, ESO 46136 might be clinging to the last wisp of the cosmic web, a ghostly reminder that even in the void, the universe refuses to let go entirely. Whatever the truth, this lonely galaxy forces us to rethink the rules. Voids aren't just passive gaps, they're active players, shaping galaxies in ways we're only beginning to understand. And as telescopes peer deeper into the great nothing, they might find more of these solitary survivors, each one a clue to how the universe's emptiest places still manage to write their own strange, silent stories. At the smallest scales, imaginable trillionths of a centimeter spacetime isn't the smooth fabric we picture. It's a seething, bubbling foam where quantum fluctuations twist reality into fleeting loops and strings that pop in and out of existence. This isn't just theoretical poetry. These microscopic tremors occurring in the universe's first moments might hold the key to the cosmic web's grand design. If filaments are the universe's bones, quantum foam could be the DNA that shaped them. Loop quantum gravity offers one clue. In this framework, spacetime isn't infinitely divisible. It's woven from tiny, discrete quanta like pixels on a cosmic screen. During the Big Bang, these quanta vibrated wildly, and their interactions might have imprinted faint density variations onto the newborn cosmos. Picture shaking a box of sand, the grains don't settle uniformly. Instead, they form ridges and valleys, patterns dictated by the initial tremors. Similarly, quantum-scale spacetime jitters could have seeded the density differences that later grew under gravity's patient pull into the cosmic web's vast filaments. String theory paints an even wilder picture. Here, the fundamental particles aren't dots but vibrating strings, and their harmonies dictate the laws of physics. In the early universe, these strings wouldn't just vibrate, they'd tangle and knot, creating topological defects in spacetime itself. Some theories suggest these defects could have acted like cosmic fishing nets, trapping dark matter into intersecting lines that became the Webb's scaffolding. It's as if the universe's tiniest vibrations composed a symphony so powerful, its echoes still resonate across billions of light years. The smoking gun might lie in the cosmic microwave background. That faint glow from the infant universe isn't perfectly uniform. Its temperature variations match the distribution of today's galactic filaments with eerie precision. Some physicists argue these fluctuations are too large to stem from classical physics alone. Instead, they could be magnified quantum noise, the fingerprints of spacetime's primordial foam stretched across the sky by inflation. But the most radical idea, the cosmic web might not be random at all. If quantum gravity or string theory's extra dimensions shaped early spacetime, the Webb's structure could be a hologram, a three-dimensional projection of two-dimensional quantum information encoded at the universe's edges. In this view, filaments aren't just structures, they're shadows of deeper mathematical truths, a cosmic braille we're only beginning to decipher. As detectors like the James Webb Space Telescope peer deeper into the early universe, they're hunting for subtle twists in galaxy alignments that could betray these quantum origins. Meanwhile, tabletop experiments with supercooled atoms simulate spacetime foam, searching for parallels between microscopic chaos and macroscopic order. The answer, if it comes, won't just explain the web. It could unite quantum mechanics and gravity, solving one of physics' greatest riddles by reading the universe's largest structures as messages from its smallest scales. In the vast thermal tapestry of the cosmic microwave background, that ancient light from the universe's infancy, there's a blemish that shouldn't exist. A patch of sky spanning nearly 2 billion light-years glows slightly cooler than its surroundings, as if someone pressed an ice cube against the fiery afterglow of creation. Astronomers call it the cold spot, and this anomaly refuses all simple explanations. Some say it's a bruise from a cosmic collision, our universe bumping against another bubble reality in the multiverse. Others argue it's the imprint of a supervoid so vast it defies physics. Either way, this cosmic cold case challenges everything we thought we knew about the universe's structure. The cold spot first appeared in data from NASA's Wilkinson microwave anisotropy probe in 2004, then reappeared in sharper detail with the Planck satellite. At first glance, it resembles the tiny temperature fluctuations that seeded galaxy formation, except this region is 10 times larger and colder than standard cosmology allows. The odds of such an extreme variation occurring randomly, less than 1 in 50. Something strange happened here, and the leading theory reads like science fiction. Our expanding universe might have grazed another universe's inflationary bubble during the Big Bang's first moments. The collision would have drained energy from that patch of space-time, leaving behind a thermal shadow, literally a fingerprint from beyond our cosmic horizon. Yet there's an alternate, equally unsettling possibility. The cold spot might mark the location of the Eridanus supervoid, a hypothesized region of space so empty it stretches cosmology to its limits. Voids normally cool light passing through them via the integrated Sachs-Wolf effect. Photons lose energy climbing out of these gravitational potholes. But a void large enough to explain the cold spot would need to be absurdly vast and pristine, far exceeding typical cosmic structures. Surveys have found underdense regions in the right area, but nothing matching the required scale. If such a void exists, it would mean the cosmic web has gaps we never imagined, cities of galaxies separated by deserts vaster than thought possible. The controversy deepens when we examine galaxy distributions near the cold spot. Some studies show fewer galaxies in the region, supporting the void hypothesis. Others find no significant underdensity, suggesting the temperature anomaly stems from something weirder. The most radical interpretation, the cold spot could be evidence of exotic physics, a cosmic texture left over from symmetry breaking in the early universe, or even a flaw in Einstein's general relativity that only manifests on supercosmic scales. What makes this mystery so pivotal is its connection to the cosmic web's fundamental nature. If the cold spot is a multiverse bruise, it implies our universe isn't just one bubble among many. It's a bubble that's touched others, leaving scars we can still detect 14 billion years later. If it's a void, it reveals gaps in the web so extreme they challenge our understanding of dark matter's clustering properties. Future telescopes like the Simons Observatory aim to study the cold spot's polarization patterns, hunting for swirls that could betray a primordial collision's telltale vortices. Until then, this frigid anomaly remains one of cosmology's most tantalizing puzzles, a cosmic Rorschach test where some see the shadow of another universe, others glimpse the abyss, and everyone agrees, whatever created this chill in the afterglow of creation, it's rewriting the rules of reality as we know them. Of all the cosmic web's mysteries, few are as baffling as the case of the missing metals. When massive stars explode as supernova, they blast heavy elements like iron, oxygen, and carbon into space, ingredients crucial for planets and life. These metals should saturate the web's filaments woven into the gas flowing between galaxies. Yet when astronomers analyze these threads, they find a startling deficit. Up to 80% of the expected heavy elements are simply gone. It's as if the universe has hidden its treasure, and the prime suspects might be galaxies so faint they're practically invisible. The culprit could be dark galaxies, clumps of stars and gas with barely any luminosity, drifting like ghost ships through the cosmic void. Unlike the Milky Way, which blazes with billions of stars, these shadowy structures may be dominated by dark matter, their sparse stellar populations producing little light. But what they lack in brightness, they could make up for in cosmic hoarding. Supernova metals ejected from brighter galaxies might get snagged by these faint traps, their gravity just strong enough to capture heavy elements but too weak to attract attention. Imagine a spiderweb coated in dew, each droplet clinging to the silk, unseen until the light hits just right. Evidence for this theory comes from quasar absorption lines. When light from distant quasars passes through filaments, it reveals not just hydrogen but traces of heavier elements, yet the amounts detected are far lower than supernova rates predict. Some filaments show almost pristine gas, as if untouched by stellar explosions. But in the halos of certain faint galaxies, spectrographs detect unexpected metal concentrations, pockets of iron and silicon, far exceeding what their megastar formation could produce. These anomalies suggest dark galaxies might be cosmic magpies, stealing metals from their brighter neighbors and locking them away in the shadows. The plot thickens when you consider how metals escape galaxies in the first place. Supernova winds and black hole jets can launch heavy elements into intergalactic space at millions of miles per hour. But without enough energy, these metals might not fully break free. Instead, they'd linger in a galaxy's outskirts or fall into nearby dark matter clumps. Simulations show that small, faint galaxies are particularly efficient at intercepting this debris, their gravity acting like a net for wayward atoms. Over billions of years, this process could strip filaments of their expected metals, leaving them oddly pristine while dark galaxies grow rich in stolen stardust. Yet alternatives exist. Some theorists argue the missing metals might have cooled and condensed into dust grains too small to detect, a cosmic frost clinging to the Webb strands. Others propose the elements were pushed far beyond filaments into the voids, scattered by ancient galactic winds so powerful they emptied entire regions. A handful of rogue studies even suggest exotic physics. Could certain heavy elements decay into dark matter over cosmic timescales, transforming into something invisible? The answer might lie in upcoming deep field surveys. Telescopes like the Vera-C Rubin Observatory are designed to detect ultra-faint galaxies, potentially uncovering legions of these metal hoarders. Meanwhile, atomic spectrometers aboard the James Webb Space Telescope can analyze the chemical fingerprints of filaments with unprecedented precision, hunting for the telltale gaps in elemental abundance. Every new observation peels back another layer of the mystery, revealing a universe where the most valuable resources aren't just hidden in plain sight, they've been stolen by ghosts. The Milky Way isn't just floating through space, it's riding a colossal current of galaxies, a filament so vast it dwarfs every mountain range, ocean, or continent we've ever known. This is the Pisces-Cetus supercluster complex, a billion light-year-long thread of the cosmic web that serves as our universal address. Picture a river of galaxies winding through the cosmos, with the Milky Way as a single droplet in its flow. But this isn't just any filament, it's the backbone of our local universe, a structure so immense it hosts over 60 massive galaxy clusters, including our own galactic neighborhood, the Laniakea supercluster. Laniakea, meaning immense heaven in Hawaiian, is a gravitational archipelago where the Milky Way resides as a tiny island among titans. At its heart lies the Great Attractor, a mysterious gravitational focal point pulling thousands of galaxies, including ours, toward it at over 600 kilometers per second. But zoom out further, and you'll see Laniakea is just one stop along the Pisces-Cetus filament, a thread that stretches from the Pisces constellation to Cetus, weaving through the cosmic void like a celestial serpent. This filament isn't a straight line, it's a meandering ribbon, bending and twisting as it responds to tugs from other superclusters and the dark energy stretching the space around it. What makes Pisces-Cetus so special isn't just its size, it's the way it shapes everything inside it. Galaxies along this filament don't drift randomly, they're guided by its gravitational currents, flowing toward dense knots where clusters collide and merge. The Virgo cluster, our nearest galactic city, sits at one of these intersections, its gravity subtly pulling the Milky Way closer even as we race toward the Great Attractor. Meanwhile, the Filaments' outer reaches stretch into realms we're still mapping, like the Perseus-Pisces supercluster, a sprawling metropolis of galaxies that mirrors Laniakea on the opposite end of the thread. But here's the twist: Pisces Cetus isn't alone. It's part of a grander pattern, intersecting with other filaments to form the cosmic equivalent of a highway interchange. One such junction connects it to the Sculptor Wall, another massive structure that funnels galaxies toward the even larger Horologium supercluster. These intersections are cosmic hubs, places where the Webb's threads tangle into knots of unimaginable density, forging the universe's largest gravitationally bound structures. Yet for all its grandeur, Pisces Cetus is also a time capsule. The galaxies within it tell the story of our local universe's evolution from ancient, red and dead ellipticals that burned out billions of years ago to vibrant spirals like the Milky Way, still churning out new stars. Some regions of the filament are turbulent, with galaxies crashing together in slow-motion collisions that ignite bursts of star formation. Others are eerily quiet, where galaxies drift apart as dark energy stretches the space between them. Mapping this structure has been a feat of cosmic cartography. Astronomers pieced it together by measuring the motions of thousands of galaxies, tracing the gravitational currents that betray the filament's hidden mass. Redshift surveys, like the Sloan Digital Sky Survey, revealed how galaxies cluster along its length, while simulations filled in the gaps, showing how dark matter's invisible tendrils guide everything we see. Now, as new telescopes like the Vera-C, Rubin Observatory prepare to scan the skies with even greater precision, we're on the verge of uncovering Pisces Cetus's deepest secrets. How did it form? Why does it curve the way it does? And what lies beyond its farthest reaches? These questions aren't just academic, they're personal. Because every time we look up at the night sky, we're glimpsing a tiny fragment of the filament we call home, a thread in the tapestry that connects us to the vast, woven heart of the cosmos. Hidden in the dense currents of the cosmic web's filaments, there are galaxies that defy every expectation, vast collections of gas with barely any stars to light them up. These dark galaxies are cosmic paradoxes, sprawling reservoirs of raw material that somehow avoided igniting into the brilliant spirals and ellipticals we're used to seeing. Imagine a cloud of hydrogen gas massive enough to birth billions of stars, yet floating undisturbed in the darkness like an unfinished sculpture, its potential locked away. Detecting these shadowy giants is like trying to spot a whisper in a hurricane. Without the glow of stars, they're virtually invisible to optical telescopes. But astronomers have a few tricks. When light from distant quasars passes through these gas-rich ghosts, specific wavelengths get absorbed, leaving telltale gaps in the spectrum like missing teeth in a comb. This is how the first confirmed dark galaxy, Himiko, was found: a colossal blob of hydrogen spanning 55,000 light-years, yet producing so few stars it barely registers against the cosmic backdrop. The mystery isn't just why these galaxies exist, it's how they survive at all. In the bustling filaments of the cosmic web, gas is constantly being tugged and compressed, conditions ripe for star formation. One theory suggests these dark galaxies might be cosmic late bloomers, their gas so pristine and undisturbed that it never experienced the density spikes needed to collapse into stars. Others propose they're victims of their environment. Perhaps the filament's magnetic fields or turbulence prevent gas from clumping, like a breeze scattering dust before it can settle. But the most intriguing possibility involves dark matter. These galaxies might be anchored by unusually diffuse halos of dark matter, just enough gravity to hold their gas together, but too weak to trigger star-forming collisions. Simulations show that in filaments where dark matter is smoothly distributed, gas can flow for billions of years without igniting, creating these starless wonders. It's as if the universe forgot to flip the switch, leaving entire galaxies frozen in the moment before creation. Recent radio telescopes like ALMA have begun peeling back the veil. By tuning into the faint millimeter wave emissions of cold hydrogen, they've uncovered dark galaxies lurking near the edges of known filaments, their gas so cold it's just a few degrees above absolute zero. Some even appear to be feeding brighter galaxies nearby, their untouched reservoirs funneling raw material into more active neighbors like shadowy suppliers in a cosmic black market. Yet the biggest surprise came when astronomers realized these dark galaxies might solve another mystery, the missing baryon problem. If filaments are threaded with countless starless gas clouds, they could account for the universe's lost normal matter, not hiding in plain sight but masquerading as empty space. Every dark galaxy discovered is another piece of the puzzle, a reminder that the cosmic web's true structure might be written in shadows we're only beginning to read. For centuries, science has operated under the Copernican principle, the humbling idea that Earth holds no special place in the cosmos. We orbit an average star in an unremarkable galactic neighborhood, or so we thought. But groundbreaking observations now suggest something astonishing. We might be living inside one of the universe's largest voids, a cosmic underdensity so vast it rewrites our understanding of location itself. This is the KBC void, a spherical pocket of space spanning over 2 billion light-years, where galaxy density drops precipitously compared to the rest of the universe. And the Milky Way, it's sitting almost dead center. The discovery unfolded like a cosmic detective story. Astronomers mapping galaxy distributions noticed an odd consistency. No matter which direction they looked, distant superclusters appeared to be receding from us slightly faster than standard cosmology predicted. At first, this was chalked up to measurement errors, but when a team led by astronomer Amy Barger and later refined by Ryan Keenan and collaborators analyzed data from multiple surveys, a startling pattern emerged. The local universe wasn't just subtly underdense. It was perched inside a void so enormous it defied statistical probability. Imagine stirring a pot of soup only to find a single, spoon-shaped bubble stretching from the surface to the bottom. That's the scale of the anomaly we're talking about. Here's the twist that upends centuries of assumptions. If the KBC void exists, it means the Copernican principle isn't just mildly violated, it's fractured. We're not in a random, average corner of space. We're floating in a cosmic desert so expansive it skews our measurements of the universe's expansion rate. This could explain the Hubble tension, that nagging discrepancy between local and distant measurements of how fast the cosmos is growing. Photons passing through our void experience less gravitational drag than those traversing denser regions, subtly altering their redshift in ways that mimic accelerated expansion. The implications are staggering. Dark energy's influence might be overestimated because we've been staring at the universe from inside a gravitational anomaly. Yet the KBC void isn't just empty space. Like all cosmic voids, it's threaded with faint filaments and dotted with void galaxies, isolated, fragile systems starved of the gas and collisions that fuel their crowded cousins. These galaxies evolved differently, aging faster and forming fewer stars like plants struggling in thin soil. The Milky Way's position here might even have shaped our history. Some theories suggest voids act as cosmic incubators, their quiet environments allowing galaxies like ours to avoid violent mergers long enough to develop stable spiral arms and perhaps habitable planets. Skeptics argue the void's existence contradicts the cosmological principle's expectation of large-scale uniformity. But newer simulations show such megavoid structures can arise naturally from rare fluctuations in the early universe's density field. The real controversy isn't whether the KBC void exists, it's how much it's distorting our cosmic perspective. Future telescopes like Euclid will settle the debate by mapping galaxy distributions in unprecedented 3D. revealing whether we're truly at the heart of a nothingness so vast it bends the rules of reality. Until then, the KBC void stands as a humbling reminder. Even in a universe that prizes mediocrity, sometimes the most extraordinary thing is where you happen to be standing. The cosmic web has woven the universe together for billions of years, but its grand design won't last forever. As dark energy tightens its grip on the cosmos, the very fabric holding galaxies together is destined to fray, and the unraveling will rewrite the fate of everything we see. Picture a spider's web stretched too thin, its silken threads snapping one by one until only tattered fragments remain. That's the fate awaiting the universe's largest structure, and the process has already begun. Right now, dark energy's relentless push is accelerating the expansion of space itself, stretching the web's filaments like rubber bands nearing their breaking point. Galaxies clinging to these threads aren't just drifting apart, they're being catapulted away from one another at speeds that will soon outpace gravity's pull. Current models suggest that in about 150 billion years, any galaxy not already bound to our local group will vanish beyond an invisible horizon, their light stretched to wavelengths too faint to detect. The filaments connecting them will stretch into non-existence, leaving behind isolated island clusters adrift in an ever-darkening void. But the web won't go quietly. Before the great snapping, filaments will undergo a grotesque transformation. As voids between them expand faster, the web's gas currents will thin to near nothingness, starving galaxies of the raw materials needed to birth new stars. Galaxy clusters at filament intersections, once bustling metropolises, will become fortresses under siege, their outer galaxies ripped away by the cosmic tide while their cores collapse into dense knots of survivors. Simulations show these clusters merging into monstrous singularities, their supermassive black holes coalescing into beasts so vast they could swallow entire solar systems in a single gulp. Yet even in isolation, these remnants won't escape the void. Dark energy's expansion will continue to accelerate, eventually overcoming the gravitational bonds holding galaxy clusters together. Stars will be flung into the abyss, their orbits dissolving like sugar in water. Planetary systems will tear apart, and eventually trillions of years from now, even atoms themselves might be ripped asunder in a hypothetical doomsday scenario cosmologists call the Big Rip. But here's the twist: the web's fate might not be uniform. Some theories suggest dark energy's strength could vary along the filaments themselves, creating fragile bridges that resist snapping far longer than expected. These cosmic lifelines might allow a handful of galaxies to remain connected, like climbers clinging to the last rope before a chasm closes beneath them. If true, the universe's final structure could resemble an archipelago of isolated superclusters, each one a lonely monument to the web that once bound them all together. The most haunting realization: this future is already written. The light from distant galaxies reveals filaments stretching taut under dark energy's pull, their galaxies streaming away in a silent, inexorable tide. We're witnessing the first act of a trillion-year tragedy, the slow unmaking of the universe's greatest masterpiece. And just as the web shaped galaxies, stars, and even us, its dissolution will shape the darkness that comes after, leaving behind a cosmos so vast and empty that the very concept of connection becomes meaningless. The cosmic web gave the universe its structure, but in the end, even the mightiest threads must surrender to the expanding night. What if the cosmic web, with its sprawling filaments and galaxy-studded strands, isn't truly three-dimensional at all? Imagine the universe playing an elaborate trick on us, where everything we perceive as depth, scale, and structure is actually a holographic mirage, a two-dimensional code written on some distant cosmic surface and projected into the void like light through a film. This isn't just science fiction. It's the holographic principle, one of the most radical ideas in modern physics, and it might hold the key to understanding the universe's deepest secrets. The theory traces its roots to an unexpected place: black holes. In the 1970s, physicist Jacob Bekenstein discovered that a black hole's entropy, a measure of its internal chaos, isn't proportional to its volume as you'd expect, but to its surface area. Later, Leonard Susskind and Gerard T. Hooft took this further, suggesting that all the information inside a black hole could be encoded on its event horizon, like a cosmic DVD storing a 3D movie on a 2D disc. Extend this idea to the entire universe, and you get the holographic principle, the notion that our three-dimensional reality, with all its galaxies, stars, and even our own thoughts, might be a projection of information scribbled onto some unimaginably distant two-dimensional boundary. Now apply this to the cosmic web. Those colossal filaments weaving through the cosmos, they wouldn't be physical structures in the traditional sense, but shadows, artifacts of deeper, more fundamental interactions happening on a flat, distant surface we can't see. Think of it like watching a movie. The characters and landscapes feel real, but they're just patterns of light projected from a flat screen. Similarly, the web's grand design could be an illusion, a cosmic sleight of hand where gravity, dark matter, and even space-time itself emerge from a hidden, lower-dimensional reality. Evidence for this wild idea comes from an unlikely source: quantum entanglement. In quantum mechanics, particles can become linked across vast distances, instantly influencing each other's states. Some physicists, like Juan Maldacena, have shown how this spooky action at a distance mirrors the way information on a 2D surface could generate 3D physics via holography. His AD/CFT correspondence, a mathematical bridge between certain quantum theories and higher dimensional gravity, suggests that the strange, entangled behavior of particles might be the glue holding our illusion of space together. If true, the cosmic web's filaments aren't just threads of galaxies, they're entangled quantum patterns stretched across cosmic scales. But how could a 2D surface create something as intricate as the web? The answer lies in complexity. A simple hologram can encode staggering detail. Tilt a credit card hologram, and the image shifts realistically, even though it's just flat interference patterns. Similarly, the universe's boundary could store information so densely that when projected, it generates the richness we see. The web's filaments, voids, and clusters wouldn't be independent objects but interconnected pixels in a cosmic image, their positions and motions determined by underlying data we can't yet decipher. Critics argue the holographic principle remains untested, more mathematical poetry than proven fact. Yet intriguing hints keep emerging. Simulations of holographic universes produce structures eerily similar to the cosmic web, with filament-like patterns emerging naturally from lower dimensional rules. And some physicists, like Eric Verland, propose that gravity itself might be an emergent force, a side effect of entropy and information flow on this hidden surface, not a fundamental interaction. If so, the web's gravity-driven architecture could be a secondary effect, like the way temperature arises from countless atomic motions we don't perceive directly. The most mind-bending implication: if the holographic principle is correct, the universe isn't just stranger than we imagine, it's stranger than we can imagine. The web's vastness, the dance of galaxies, even our own sense of depth and scale, all might be layers in an illusion, a cosmic matryoshka doll where every layer points back to a deeper, simpler truth. Future experiments, like high-precision measurements of quantum entanglement or gravitational waves, could look for telltale pixelation in spacetime itself, tiny, fundamental grains that betray the universe's true, flat nature. So the next time you gaze at the night sky, ponder this: the glittering tapestry above you might not be the full story. Behind every star, every filament, every void, there could be a hidden code, a two-dimensional whisper from the edge of reality, weaving the grand illusion we call the cosmic web. And if we ever learn to read it, we might just crack the universe's ultimate cipher. From the quantum foam that birthed the cosmic web's filaments to the dark rivers of gas feeding galaxies, we've uncovered 30 mind-bending secrets that rewrite what we thought we knew about the universe. We've traced ghostly magnetic fields threading the void, watched supermassive black holes sculpt the Webb's architecture, and even glimpsed the possibility that our entire reality might be a holographic projection. The Webb isn't just a structure, it's the universe's operating system, shaping everything from the birth of the first stars to the fate of galaxies trillions of years from now. Consider how these revelations reframe our place in the cosmos. We're not just inhabitants of a lone spiral galaxy, we're passengers on a filament flowing toward the Great Attractor, part of a billion light-year superhighway that connects us to the largest structures in existence. The atoms in our bodies were forged in stars that formed along these threads, carried across epochs by the Webb's invisible currents. Even now, dark energy is stretching this tapestry apart, reminding us that the universe is a dynamic, ever-changing masterpiece, and we're witnessing just one fleeting frame of its grand story. So, which secret reshaped your cosmic perspective? Was it the discovery of filaments hotter than the sun, or the lonely galaxies adrift in voids so vast they defy logic? Maybe it was the realization that the Webb's blueprint was encoded in quantum fluctuations moments after the Big Bang, or the chilling possibility that we're living inside a void that distorts reality itself. Every thread we've pulled unravels new questions, proving that the deeper we look, the more mysteries emerge. The journey doesn't end here with telescopes like Euclid and the Vera C. Rubin Observatory set to map the Webb in unprecedented detail. We're on the verge of even greater revelations, so tell us which secret left you in awe. Drop your thoughts in the comments, and if you're hungry for more cosmic wonders, hit subscribe. The universe still has countless stories to tell, and we're just getting started.